In analytics, we use data to answer our questions of interest. To do so, we need to get our data into the right form, and this very often involves joining together or merging different data sources.
In the world of the Transformers, nothing is what it seems. Meet the Constructicons, 6 evil robots that transform into one mechanical giant.
The Transformers, more than meets the eye. The Transformers.
It's Devastator, 6 Constructicons in 1.
Transformers,
Devastator's
more than
attacking.
meets the eye.
Constructicons gift set sold separately from Hasbro.
I think we can help. Merge into Devastator!
Like I was saying, in analytics, we use data to answer our questions of interest. So we need to get our data into a form where analytics can happen. And very often, this is going to be what you spend 80 to 90% of your project time doing. So this does usually involve joining together or merging different data sources. And in this video, I want to talk about how we can gather up all the sources of information we want to use in our analytics and to work with them. For example, if we're working for a telecommunications company, we might want to dive into our data to figure out what type of customer is the most likely to churn. Do we have to watch out for married customers or single customers? Do people with incomes between $60,000 and $70,000 have a higher rate of churning than people with incomes between $100,000 and $150,000? If we're working for the development office at a university, we might want to predict the amount of money alumni will donate next year based on their major, their graduation year, and how they've been interacting with emails. If you're working for Kroger, you might want to study the effectiveness of different coupon campaigns and how that might vary based on product and customer demographics. To do analytics, the data needs to live in what we call a flat file, basically like a single Excel sheet. Each row corresponds to some entity we're studying, like a customer, a transaction, car, or a song, and the columns record characteristics of those entities, like their age and income if we're talking about customers, price and quantity if we're talking about items, fuel efficiency and horsepower if we're talking about cars, or the artist, beats per minute, and key if you're studying songs. Unfortunately, very often, the data that you need to answer your question is dispersed or stored in multiple different data sets. Take, for example, the telecommunications data, which you can find a link to in the description of this video. We have a file that contains demographic data on the customers, like whether they're a senior citizen or single. We have another file for each customer that contains details about their plans. And finally, another file that gives additional information about the customer, how they pay, how much they owe, and more importantly, if they churned or not. So we can't really do analytics with this directly. If I wanted to know the fraction of females who have streaming TV that have churned, I'd need to find some way to combine these data sources so that my data looked like something like the following. We'd have essentially a couple columns, one giving us the customer ID, another the gender, another letting us know if they do streaming TV, and then finally a column that lets me know whether they did or did not churn. If I had that data, then the answer can be found pretty easily. Just take a subset of customers that are females with streaming TV and look at the fraction of churners. So the goal of this video is to show you how to combine disparate data sources so that analytics can happen. We're going to be on the hunt for a flat file that's going to let us do analytics, and we want to learn how to get there. So we'll discuss two major operations. The first is binding rows, or sometimes called stacking or taking the union of different data sources. And this happens when the two data sources look basically the same and we just need to append the rows of one table to another. And really more importantly, merging, also referred to as joining. This happens when you need to essentially put information from one data set into another, like putting in the customer's gender and streaming status into the table that let us know if the customer churned or not. Now let's learn how to do these operations in the tidyverse. Your best resource will be the data transformation cheat sheet, as well as other general cheat sheets about the tidyverse and dplyr. And first up is going to be about row binding. So let's look at a collection of data files that come from Spotify. Each of these data files contains information about some of the more popular songs of the decade. And we have a file for each decade from the 1950s to the 2010s. And you can find a link to these files in the description of this video. Now, to combine them all into one file, we need to stack them. Basically, we want to open up the data for the 50s, then add the songs from the 60s to the end of that, then add the songs from the 70s to the end of that, the 80s to the end of that, so on and so forth. Now, the command we're going to use is bind_rows from the dplyr package. So let's go ahead and load up the tidyverse and the dplyr package with library tidyverse. All right, let's get the data read in and see how this works. And we'll start out by running a series of read.csv statements, saving each data set to its own data frame in R. Now let's use the head function of the songs 50 data to explore just a little bit. What do we have? We have the title of each one of these songs, the artist, and the beats per minute, the duration in seconds, and then also the energy level of the song, a metric that Spotify uses some data analysis skills to figure out how energetic that song really feels. So remember when we use the pipe command, the %greater pipe, we can always get that very quickly on a Mac or on a Windows by either doing the Shift Command M on a Mac or the Shift Control M on Windows. So running songs 50 pipe head lets us see the first 6 rows of the data frame, and the other files that we've loaded in basically have the same structure. We run the same line of code for the songs from the 2010s. We have the title, the artist, beats per minute, duration, and energy once more. So what we'd like to do is we'd like to add the rows of the 1960s data to the data frame for the 50s. And we're going to use bindrows to do that. And it's going to work pretty much like what you would expect. Our function is bindrows, and the 2 arguments, at least for this operation, are going to be the 2 data frames that we want to stack on top of each other. Songs 50 is what we're going to start out with, and we're going to add to the end of that songs 60. So if we run this as a command, it'll print it out to the screen, and we can go up and down to verify that, yeah, this looks like it stacked it up. And so we can generalize this and get all of the data files on top of each other by just putting in the names of every single one of the data frames into the bindrows command. Now doing this once again, we'll print it to the screen and we're looking and it's in the right form. We see that each one of these data files have the same structure. But one thing that's not the most optimal about this presentation is that we don't have a column that lets us know what decade each of these songs actually belong to. After all, if we want to see if there are any changes in energy or beats per minute across the decades, we're going to have that as an additional column that encodes the decade information. So, mission accomplished, but it would be nice to know what decade each song belonged to, and there's 2 ways to really add in this information, an additional argument that we can add in to bind rows. So what this additional argument is by adding a comma after your data frames and adding in .id equals, and then in quotes, giving it the name of the column that you want to add that contains where the data came from. So if I do .id equals decade and pipe this through head to look at the first 6 rows, we can see that it's added a column called decade, whatever I had in my double quotes. But this isn't really the most optimal either, because if I pipe this through the tail command, I'm noticing that I'm not really getting the 1950s, the 1960s in the decade column. I just get 1, 2, etc., corresponding to which data frame it was referring to originally, which argument in the bind rows command. So how could we fix this? What if we actually wanted to get an actual column that let us know what data frame the data actually originally came from? Well, what we can do is we can wrap the data frames that we're binding together inside the LST function. So watch what happens when I run bind rows applied to LST of songs 50 and songs 60. Now I've created that column called decade, and it's letting me know what the name of the data frame was, where this row originally came from. So these are all the 1950s songs. If I look at the tail of this, I can see that, yes, I have that column letting me know what decade this corresponds to. So let's bind all of our data together and create a new data frame called songs. We'll save the output of running bind rows. We'll left arrow that to a data frame named songs. And let's just look at a random sample of 20 rows from that just to make sure that it looks like our data is in a good place. So scrolling up and down, we see that the ID column is letting us know where the data originally came from. We have the title, the artist, and the same 3 columns that we originally started with. Now, if you wanted to change the name of this column, right now it's ID. Remember, just in quotes, that's where you're going to actually put in the name of that column. So if I were to change this from ID to decade, what I would find is indeed that new column is called decade. We could actually do some sort of analytics at this point. We might have a question like, are there statistically significant differences in, let's say, the average energy of songs across decades? Now, if you were a UT undergraduate who took BAS 320, you've used the reg class package to answer questions like this with the associate command. Let me go ahead and load up the library reg class package. And in that package, there's a command called associate that looks to see if there are any statistically significant differences in averages across different groups, our groups being the decade that we're comparing the songs. What this will do is it'll give us some text output that tabulates what the average is for each one of these different decades. So this is the average energy for the 2000s, the 2010s, the 1950s, etc. We see visually that there's a substantial difference across these different decades. Now, we don't expect these averages to match up exactly when we go and collect data. We expect there to be some difference, and so we look at the p-value to determine if there are any statistically significant differences. And this p-value is much less than 0.05, so we can say pretty definitively that not all decades have the same overall average energy. There's at least a couple differences across the different decades. This analysis doesn't tell us where those differences actually are, just that there are some differences. Now, bind rows is actually really quite flexible when you start giving it different data frames. If the columns don't match up exactly, no big problem. There's just going to be NAs placed accordingly where it couldn't find a match. So, for example, let's imagine that I just had 2 data frames. Let's call them set 1 and set 2. These are 2 different data sets looking at 3 different students, their GPA and how many sports they participated in. Data set 2, 3 other students, their GPAs, but then the number of honors classes that they've taken. We have a column mismatch here because the columns in set 1 aren't quite the same as the columns in set 2. But if we run this through bind rows, it'll figure out what to do. So it'll still stack those 2 data sets on top of each other, and it'll just put NAs into the sports and honors column appropriately when it couldn't find entries in that column in one of the data frames. Now, it's fairly rare that you'll run across data like this and you have to row bind the files. A much more common scenario is having to merge information across multiple data frames, like with the telecommunications data. Once again, you can find a link in the video description. Let's go ahead and open up the churn.csv and customer.csv datasets in Excel and talk about what we want to have happen. Basically, what we'd like to do is to take the churn.csv, which contains information about a customer's history and payment, and add in additional columns, giving that customer's gender, if they're a senior citizen, if they have a partner, and if they have dependents, information that's contained in customer.csv. Now, we're able to match up the rows across these 2 different data files by the customer ID, which we refer to as the primary keys in both tables. They're all unique from one customer to another. So how do we do this? Well, let's get comfortable with the idea of merging together different data sets with a smaller, easier to digest example. So let's create a smaller set of data that's going to give us some insight here. I'm going to create a data set called churn, which looks somewhat like the churn.csv data file that we have. We have a column giving the customer ID, the tenure, how many months they've been on contract, their total charge, and if they've churned or not. And then also let's go ahead and define a data frame called customer. And if I were to go and look at what's inside the customer data frame, what I have are the customer IDs, their gender, if they have a partner, and if they have dependents. And then finally, I'm going to define a data frame called Internet that is going to have a column that gives me the customer ID and then also whether or not they subscribe to any of these streaming TV services. Now, by design, you'll notice that the set of customers aren't quite identical across these three different data frames. We have customers A, B, and C in churn, whereas in customer we have A, B, and D. And in Internet we have A, C, D, E. So there's a bit of a mismatch in terms of the types of customers that we have across these three different data sets, and we're going to have to keep that in mind as we learn about how we join the different data sources together. So let's go ahead and start with the churn table. And what I'd really like to do is I'd like to start out with the churn data frame with customers A, B, and C. And when available, add in information that's contained in the customer data frame about their gender, partner, and dependents when it's actually available. We see we don't actually have information about customer C in the customer data frame. All right, so how do we do this? Well, in the tidyverse and dplyr, this is accomplished with one of the join set of functions, of which there are actually four. There's a left join, a right join, an inner join, and a full join. Now, let's go ahead and start out with the left join, which I feel seems to be the most common, or at least the one that I tend to use the most. So let's go ahead and start out with churn and pipe that into the left join function where we're going to extract out information from the customer data frame. I'm just going to run this and we're going to talk about what the results look like. So what just happened? Looking at the results, we've indeed added the gender, partner, and dependents column from customer to churn, but customer C, which was in churn but not in customer, has NAs added since no information about customer C was in the customer data frame. And that's how I like thinking of a left join. We start with a data frame, then merge in information from the other when available. All rows in the data frame that we start with survive the merge in some sense. Now, how does this command know how to match rows from one table to another? Now, that's going to be the job of the by argument, and I've found it easiest to give the by argument the join by command and then tell it which columns are used to match the rows. Now, there is a special requirement on this column in the data in the join function, namely it needs to be the primary key of that table. In other words, each value in that column should be unique, so there's only one match. Now imagine there was a data integrity issue in the customer table, and for whatever reason, two customers had the same ID. In bad customer, we see two customers with the ID B. They have different genders, different partner, different dependents entry. Now, the join will still run, but the issue is going to propagate along with it. Running the left join function, piping churn into left join using bad customer, we see that the output is a bit puzzling. We do have two entries for customer ID B, but different genders, different partner, different dependents. So this is a good lesson. Before you start joining together different data sources, make sure each table is clean and free of integrity issues. Garbage in, garbage out. A few more things about the joins. First, if it happens that the columns you're using to match have the same name, you can simplify the command by having that common column name in the join by statement. And that's the case here. The customer ID column is the same with churn versus customer. So when I run the by command, I only need to put join by customer ID. R is going to figure that out and say, okay, well, these two columns have the same name, and the join is going to run just fine. And if it actually just so happens, if that column is the only one in common between both tables, you can actually omit the by argument entirely. Since customer ID is the only column in common between churn and customer, we can just say churn pipe left join customer. It'll figure out that, okay, we need to join this by the customer ID column, and the join is going to run absolutely flawlessly. Now, finally, it might be the case that to match up rows, you have to match up values across two or more columns. And that might be the case when the data frame doesn't actually have a primary key, but two columns need to be combined in order to uniquely identify the rows. Now, let's illustrate this. how we're going to use this composite key of two different columns by defining two small data frames, one called people and one called stats. Let's look at what both of these are. And what we have is that people contains information on 5 different people, their first and last name, and their score on some exam. And then we have a second data frame called stats, 2 columns, first name and last name, and then also the number of pets and the number of cars those individuals have. Now, if we wanted to start with people and add in the information from stats, namely the number of pets and the number of cars, we couldn't just match on the first name since there are duplicate atoms, and we couldn't just match on the last name since there are duplicate Petries. Neither first nor last names by themselves uniquely identify a person. Now, if I try to run this code anyway, it'll still run, but it'll give out a warning message that's a bit cryptic, and actually looking at the output, we see that it's rather nonsensical. We have first Adam, last Petrie, score 91, last name Petrie, pets 2, cars 1, but then another Adam Petrie with the last name Warner. Something is up. This isn't really working out. So rather, we need to match based on the combination of first and last name. We need a composite key for this table when we're performing the join. And this is easy enough. All we need to do is add additional arguments in the join by function. So if I wanted to join by a combination of columns, I could start out with people and then pipe that into the inner join function. I'm going to take the information from the stats table. And the way that I'm going to match the rows back and forth is not by just one column, but by 2 columns. So in the by equals join by function, I'm going to let them know, okay, how do we match these columns? The first column in people matches the first name column in stats. The last column in people matches the last name column in last. And so since I'm giving 2 different columns in the join by function, it's going to use the combination of values in those 2 columns in order to match up the rows back and forth. So when I run this, we can see that it runs flawlessly and I get a data table that I expected. So what about these other joins? Well, let's talk about a right join. So if we go ahead and run churn and pipe that into right join with customer in the argument, let's see what the result is going to be. In this case, what we have is information on customers A, B, and D, and those were the customers in the customer data table, the one that I actually put inside the right join function. And so that's what a right join is going to do. It's going to make sure that all of the rows in the table inside the right join function survive the merge. And if we can't find a match with the table that's on the left-hand side of the pipe, NAs are going to be placed in those columns from the table on the left of the pipe. So we have information on A and B in common between churn and customer. Customer has ID D, but D does not exist in churn, so their tenure and their total charge and their churn status are going to be replaced with just NAs because we couldn't find a match. Now, in general, I personally don't like right joins since normally when we're merging data sources, we're starting with a particular table in mind and then adding columns from a different data set. And we want all the rows in the table we're starting with to survive. Thus, I think left joins are preferable. Right joins is kind of a weird way to think about the joining operation. Now, what about the inner join statement? Well, what's the result? We see information only on customers A and B. And this is what an inner join is going to do. Only the rows that are in common between these 2 different data tables are going to survive. So the only customers that survive this inner join are customers A and B. C is in churn, but not in customer. D is in customer, but not in churn. So only A and B are in common. Those are the only 2 rows of my output. And then finally, what is a full join going to do? Well, once again, we'll print out the churn data set. And for this one, I'm going to do a full join with the internet data set. All right, so churn still has that information about customers A, B, and C. Internet has information on customers A, C, D, and E, along with their streaming service. Notice that there are 2 customers in common, A and C. Churn has information on customer B. Internet has additional information on customers D and E, which we don't find in churn. So if I go ahead and pipe churn through the full join function with internet as the argument, notice that the column names don't match up exactly, so I have to pass the join by function. What's the result going to be? Well, in this case, every row on both the different data tables are going to survive the merge. And when it couldn't find the corresponding row, NAs are just going to be placed there instead. So you'll notice that we have information on A, B, C, D, and E. Those are all the customers across both tables that observed. Now, we didn't have information about customer B in the internet table, so streaming TV is NA for them. And likewise, we didn't have information on customers D and E in the internet table, so we have NAs for their tenure and total charge and churn. Now, full joins seem to be relatively rare in analytics. I've found them most useful when examining where data is missing and if there's any patterns or to identify data integrity issues or anomalies across tables. Normally, missing values and data issues are handled on each table separately before you try to merge sources, so I don't really see full joins come up all that often. Really, in analytics, it's the inner join and the left join that tend to be the most popular. All right, so now that we know how these joins work, let's go back and revisit the full telecommunications data set. So let's read in the data sources, and you can do this either by getting the files locally on your computer or actually by reading it from the Google Sheet, which is kind of a neat way to share smaller data sets like this. You can find the code in the video description. And so once we've run these 3 read.csv commands, we have the full churn data, the telecommunications data in the environment. So here's what I would like to do. I want to estimate the churn probability of women with streaming TV services. Now, my best guess from the data will be the fraction of females who have streaming TV that have indeed churned, but I need to merge the 3 different data sources together since gender's in one table, streaming TV in another, and the churn status in yet another. Now, looking at the global environment, we see that each one of these tables has 7,043 rows. Now, that could be a coincidence, but most likely these 3 tables all contain the same set of customers. But let's check. So how can we do this? Let's start out by comparing the sorted vector of customer IDs to see if they are all the same for each table. So what I'm going to do is run the all command, and what I'm going to pass to the all function is the sorted list of the customer IDs in the churn data, and I'm checking to see if those are all equal to the sorted list of customer IDs from the customer data table. And running this command, I find that it's true. So yes, all of the IDs are in common. And I can do the same sort of thing just looking at the customer IDs in the churn data data table and the internet data table. Running that command, I find that yes, all of the customers across these 3 different data tables are identical. So we actually have some pretty good news. It actually doesn't really matter which flavor of join we use to merge in these 3 different data sources. They're all actually going to provide us with the same final result. So for this example, I'm going to use left join, since if I didn't already know that I didn't have to worry about which join to use, this is going to let me keep all customers with the known churn status in the churn data frame and add additional information about them when available. And if there were any NAs in that information, I could strip that out later. So what we're going to do is we're going to start out with the churn data table and then pipe that into the left join command with customer data to add gender. Let's go ahead and save the output to a table named final. And then what I want to do is take final, which I just created, and pipe that into internet data to add information about the customer's plans. And I'll just redefine final as the output. Of course, if you don't like 2 separate commands to do this, you could always streamline this actually with double pipes. So we could take churn data, pipe it into the inner join with customer data, pipe that into the inner join with internet data, and this is going to provide us with the same data frame called final. Information that's complete about every customer that we're looking at. So let's go ahead and just look at the first few rows of the final data frame, and we see that we were successful. We have a column for customer ID, the number of months they've been in contract, if they have phone service, stuff about their plan, what they're subscribing to, how they're paying, charges, demographic information like gender, senior citizen, etc., and also streaming TV, something that we were interested in. So now back to the original question. What fraction of women with streaming TV have churned? Now, to actually answer this, we need to look ahead just a little bit to some commands covered in the next video, where we go a bit more into dplyr, namely how to take subsets. So in dplyr, we take subsets using the filter command, and the syntax is fairly straightforward. We'll also use the select command to only keep track of the churn, gender, and streaming TV columns because we see that there's a lot of columns in that final data frame that we had constructed. So what we're going to do is we're going to take final and pipe that into the filter function. We're going to take a subset. What rows do we want to have in our subset? Well, we want the ones where streaming TV is equal to yes. Double equal sign is going to check to see if that's equal to the word yes. I put that in quotes. And then I'm going to pipe that into another subset. I'm going to pipe that into the filter command where I just extract the rows where gender has the word female in that column. And then just to simplify, I'll pipe that into the select function, which is only going to have us keep track of the columns that I specify in that function. So we'll kind of filter out, we'll take out the extraneous columns. We're only going to keep churn, gender, streaming, and TV. So running that command and looking at the first few rows, we see that we've done our job. So we have the correct subset. We have a column for churn, for gender, streaming TV. We actually don't need gender and streaming TV anymore because all of the people in our data set are females and they all have yes for streaming TV. So we're ready to come up with our estimate of the churn probability for this group. Now, if I get a table of the entries in the churn column, I find that we have 402 churners. And out of how many? That's going to be our estimate of the churn rate. If I divide 402 by the nrow command, that'll let us know how many customers we had in that subset, we find that our best guess for the churn probability is just under 30%. Now, there's another really cool way to do that when we're estimating probabilities, and that's to use the mean function on some logical condition that we're interested in, the probability of some event that we want to estimate. So, for example, if I ran the function mean subset $churn double equal yes, it'll dive into the churn column of that subset table and report back the fraction, somewhere between 0 and 1, of those entries that are equal to yes. So we get out that same value, a little bit less than 30%. Now, how does this compare to the overall churn rate at this company? If we go back to our final data table and look at the churn column, what fraction of entries equal to yes, we find that the overall churn rate in the data is right at about 26.5%. So for women that do have streaming TV, it looks like that churn rate might be just a little bit higher. Now, while we're on the topic of adding new columns to our data by merging in information from another, let's talk about the mutate command. So mutate is going to allow us to create a new column in our data by performing arithmetic or other operations on the columns that we already have. For example, we might want to add a new column that gives each customer's average monthly charge, taking the total charge and dividing it by the number of months that they've been on contract, the value in the tenure column. Now, to do this, all we need to do is come up with a name for this new column and set it equal to the calculation that we want inside the mutate command. So let's look at this. Let's start with final and pipe that into mutate here. So final pipe, and inside the mutate command, we'll write out average monthly charge. That's going to be the name of our column. And we're going to set that equal to the value in the total charges column divided by tenure, the number of months they've been on contract. So once I do this, that'll just print out everything to the screen, and we can see that we've added that column to the end of that. But let's get a more streamlined version of this. Let's only keep the total charges, the tenure, the average monthly charge, and the monthly charges column so that we can compare monthly charges with average monthly charge. So I'm going to take final, pipe that into mutate to create that column, and pipe that into the select function just so that I can look at those specified columns. So when I do this scrolling up and down, I find that the values inside that new column that I created, that average monthly charge, match up pretty well with the value in the monthly charges column. But as we know, plans can increase in price. Customers may change what type of services they're subscribed to. So it's not too surprising to find a little bit of discrepancy sometimes in the overall average monthly charge, the total charge divided by the number of months they've been under contract, and their most recent monthly charge. Now, these computations behind the new columns you want to create can be as complex as you'd like, and you can actually use the mutate function to add more than one column at a time if you really want to. So for example, let's create a categorical variable named long-term that is either yes or no, depending on if the customer has been under contract for 24 months or more. If I look at the first 10 values of the tenure column in final, I see that customer 1 has only been under contract for a month. Customer 2 has been under contract for 34 months. They would be one of these long-term customers. So how could we add this categorical variable, yes or no, that lets us know if this customer is long-term or not? So for this, we're going to use the ifelse function to help us out. Now, inside the ifelse function, the first thing that we're going to put is a logical condition that we'll use to create these new values, the yeses and nos. So what are we looking at? We're looking to see if the value inside the tenure column is at least 24. So first argument of if else is your logical condition. And the second argument is what value you want to have output when that condition is true. So if their tenure is at least 24, yes, they are a long-term customer. So we'll have yes in quotes. And the third argument is going to be what you want the output to be when that logical condition is false. If that tenure is less than 24, we want them to have the word no in that long-term customer column we want to add. Now, we'll wrap that inside a factor function so that R treats it as a bona fide categorical variable. And let's go ahead and pipe this into the head 10 function so that we can make sure that our work looks legitimate. So customer 1, no. Customer 2, yes. No, yes, no, no, etc., etc. So yeah, every time we see a value 24 or larger, we get a yes out. And if we see a value less than 24, we get a no out. So what we could do is we could also add this column with the mutate command. And this is where we have to worry a little bit about how clear our code is that we're actually writing. So if we were to take final and pipe that into mutate, I can add in more and more columns just by separating each column in their computation. So I could say mutate average monthly charge equals total charges divided by tenure. That's the column I added before. And then put a comma and say, okay, and then also add in a new column called long term, which is the result of running factor on that if else function to see if their tenure is at least 24 or not. So, I could do it this way, but that's a really long line of code, and we're always trying to design our code to be readable and understandable so that we can understand it if we go back to it, other people can understand it if they're looking at it for the first time. So really what we should do is something a little bit more readable like this. Take final, pipe that into a mutate function where we create that average monthly charge, then pipe that into another mutate function where we create that long-term column. And just so that we can check our work, let's go ahead and pipe that into the select function where we look at the columns that we've been working with just to double check our work. We'll go ahead and look at the first 10 of those rows by piping the result into head 10. And so there we have it, the total charges, the tenure, the average monthly charge that we created, the monthly charge, the last month's charge, and then also if they were a long-term customer or not based on their value of tenure. Brilliant. And so there you have it, a quick overview of how to combine multiple data sources, either with a join command or a bindrows command, depending on your data tables are set up. And you also know how to create new columns from columns that you already have. So once you've mastered these skills, you're going to be able to get your data into a flat file where analytics can happen, but don't necessarily expect that to come super easy. I'm very fond of saying that between 80 to 90% of the time you spend on any analytics project is going to be spent in data wrangling land, where you're going to be performing these data integrity checks, combining different data sources together, creating new columns, doing some feature engineering. But once that is all done, we can start having fun playing around with the data and extracting some actionable insights. So until next time.